Hi, my name is Prem Gopalan. I'm going to be talking about Bayesian Nonparametric Poisson factorization for recommendation systems. This is joint work with Francisco de Ruiz, Rajesh Ranganath, and David Bly. Okay, recommendation systems are everywhere. These are just a few examples. They're quite well known. And what's the problem? So these systems, what they have tried to do is uncover user behavioral patterns from a population of users and use these patterns to recommend to specific users. And a couple of things that they really want is scalability, because data is growing at such a rapid rate. But they also want good top-end predictive performance. What do I mean by that? Among the other things that they want. So top-end recommendations are very common. If you're reading a New York Times article, you see this on the right-hand side. These are 10 articles that New York Times desperately wants you to click. So the hope is that by giving you some recommendations, New York Times hopes that you will click and read, and so forth. So as we can formulate this as a machine learning task, in which case we would design a test set that has some of the articles that the user has already read. And then we would count the number of these articles that are also in the test set. So common metrics like precision and recall can effectively measure this kind of performance. But this is a difficult problem, because if you look at the real-world interactions, they commonly follow power law distributions, where a small number of users consume or rate a very large number of items, and then most of the users tend to lie in the middle or consume very small number of items. Here are 4 different data sets. Some of them are implicit, in which case that New York Times, for example, the user has just read an article. He's not rated it necessarily. Netflix, of course, it's movie ratings. Mendeley is also a kind of implicit data set, where we have scientists who each have a user library of articles. So all we know is that these scientists have these articles. So what's the current state of the art? There are a lot of probabilistic modeling approaches, but they have some limitations because they use complex methods to handle missing data. By missing data, I'm referring to the data in the matrix, in the user item matrix, that's not observed. And they often have intractable model selection. So you'll have to specify the latent dimensionality, for example, in matrix factorization. You have to repeatedly run these models with different settings of that latent value. And frequently, we've been seeing in the literature that they evaluate root mean square error. But as I've just motivated, you might be more interested in top-end prediction. So in this talk, I'm going to talk about this model that we developed, which has the following goals. We wanted to scale to massive data sets. We wanted to adapt the dimensionality of latent components to data as it sees the data. And it needs to have better precision and recall, or at least as good as current methods. A little bit of background. So some of the common approaches are based on matrix factorization. So how does matrix factorization work? The idea is to represent the users and items with low-dimensional vectors, each of size k, and the affinity between a user and item is simply the dot product theta u transpose beta I. And Gaussian matrix factorization is a common approach, where what we're doing is we are optimizing the mean square difference between the observed rating and theta u beta I, and coupled with quadratic regularization terms. And now it can be shown that optimizing this objective function is the same as computing maximizing the log posterior over the user and item latent vectors with the hyperparameters held fixed under a Gaussian model. But note that the summation is over only the ratings that are greater than 0. So on explicit data, that's fine. All you're seeing is that the user has rated these items. So commonly, these methods do not include the missing data in the objective. So in the literature, map estimation has been shown to scale well. And also, there are approaches that use MCMC leading to full posterior distributions over the user and item latent vectors, and this gives even better RMSE. But again, the limitation is that they do not make use of missing data, which has recently been shown to be essential for good top-end predictive performance. And this is what we find on real data sets. Moving to implicit feedback, where the user has not explicitly rated items, this is an even bigger problem. Because as before, we cannot simply omit the missing data. You've got to patch it in some ways. You've got to include it in some ways. Because if you omit it, you're going to seriously bias the user profile. Commonly, two approaches are taken. You can either try to downweight the effect of these missing data. So you interpret them as zeros, and then you try to balance the effect of these zeros in the optimization problem. Or you can generate negatives from this missing data by subsampling. But both methods have problems. In the former method, you got to introduce confidence weights, and you got to fit these confidence weights using cross-validation and so forth. It's quite expensive. And in the subsampling approach, it's not clear how many zeros or how much of zeros to compensate for. Some approaches have tried to balance the negatives to observed ratings. This works under certain metrics, which also have balanced test sets. But if you have a highly unbalanced set, then it's not clear how well this will work. So our idea is to step back and say, well, what's going on here? How can we capture what's going on with missing data? What's the primary source of missing data? And the answer is, we think the answer is, the users have limited resources. You have limited time to watch movies. You have limited money to buy products on Amazon, and so forth. So a good model should capture this limited budget of users. And our approach is to use Poisson factorization, which is a probabilistic model of users on items, where YUI, which is the observed rating, is drawn from a Poisson distribution parameterized by the inner product of the latent weights associated with users and items. Now, the only difference from matrix factorization that we just talked about is that these vectors are non-negative. And we also want them to be sparse, so we place gamma priors and set the hyperparameters appropriately. OK, so how does Poisson factorization capture a finite user budget? It's quite simple. We can actually rewrite the generative process as a two-stage process. First, the user draws the total amount of ratings, or the money, or whatever the quantity is, from a Poisson distribution. And the parameter is simple to understand because the sum of Poisson's random variables is another Poisson with rates equal to the sum of the rates. So that's why you end up with theta u transpose sum of beta I. And then the user decides to distribute his budget across all of the items. And that's this vector yu1 to yum. Let's assume that there are m items. And we can show that that's multinomially distributed with the total count set to his budget bu. How does this help? Now, it turns out with this property, the Poisson model is less surprised when someone does not watch movies. It does not penalize in the same way as a Gaussian model does. For example, let's say you watched Star Wars and you rated it 5 stars, but you did not watch Empire Strikes Back. And let's assume both movies have the same betas, which is the same latent vectors, attributes. They're both science fiction movies, have to do with Star Wars and so forth. Under the Poisson model, it has a large gain in bringing a user closer to these movies, and it only is penalized less by a small amount because the user did not really watch Empire Strikes Back, which happens to be in the same topic. Again, another way of saying it is it's less surprised that you did not watch a movie that you have an affinity for, or the topic that you have affinity for. We can try to experiment with this in practice. So from the Bayesian statistics literature, we can use the posterior predictive checks to see if indeed the Poisson model can capture, Poisson factorization model can capture the user budget of users. So what we did was to fit this model, and then draw a replicated data set from this fitted model. The replicated data set will have the same dimensions as your original data set. So here we use Netflix, so we have 100 million ratings. So we go back and say, well, draw me a matrix with having the same number of users and items. And then we count the number of ratings each user has totally expended. And that's the user activity in the x-axis. There are 3 lines here. The square boxes show what the observed user activity was. The red line is what Poisson factorization is the one that we get from the replicated data set. And the blue line corresponds to Gaussian matrix factorization. So we used a version from Gopalan, which uses matrix factorization with bias terms and fits it using stochastic gradient descent. And as you can see here, the Poisson factorization does indeed capture user budget well. For simplicity here, I show just one replication. We've done multiple replications, and the variance is not as high. Another property is if we write down the likelihood of observed data, we find that the likelihood is a function of only the consumed items. So even though the model generates both the zeros and the positive ratings, the likelihood turns into a function of only the consumed items, which means that if you're optimizing this, you only need to iterate over the positive ratings, which is very good. So in practice, we find pretty good predictive performance on large data sets. And I'm not going to go into the details other than to say we did compile with LDA matrix factorization and non-negative matrix factorization, and we used mean recall and mean precision as metrics. And this work is up on arXiv if you want to take a look at it. But in this paper, we focused on, well, there's still a huge limitation, which is finding the best latent dimensionality is expensive. We'll have to set k to different values and rerun this model. So we want a model with support over infinite k, such that the posterior distribution can capture the effective k. So how do we go about doing that? So our thetas and betas are now infinite dimensional non-negative vectors. But we still want the expected parameter of the Poisson distribution to be finite, because the ratings are finite quantities. If you assume that beta ik or IID, that's the same as saying, well, we want the expected sum of the thetas to be finite. And a natural way to do this, which is to get a countably infinite set of positive weights, is to use a gamma process. What's a gamma process? It's a completely random measure with a component that has Levy measure as an equation 1. So what we end up doing is we are drawing points from a Poisson process that has mean measure set to this Levy measure. And the Poisson process, the points, we can define them as having locations Li and weights Wi. Because the intensity of this process is infinite, we end up with an infinite, countably infinite number of points of atoms, essentially. So that satisfies one of the properties we want. The other property is if you look at the marginals under this random measure, they are gamma distributed with shape set to h of omega, where h is the base measure. Now, if you assume the base measure h is continuous and finite, again, we know b of omega is finite, which satisfies the other property that we want the total sum of the weights to be a finite quantity. So there we go. These are the weights that we want, which are the weights of a random measure drawn from a gamma process. Now, we could use a Poisson process to simulate this, but another simpler direct approach is we can actually use the stick breaking construction of a Dirichlet process and scale the sticks with the gamma random variable. And this has been shown to give us a draw from a gamma process. So that results in the following generative process, where you have n users and m items. And in 1.1, we draw this total user weight, BU, which we know that the marginal is a gamma distribution, so we draw the total user weight from a gamma distribution. And the next following 2 steps are simply the stick breaking construction of the Dirichlet process, except to set the weights theta uk, we scale the stick by BU. And steps 2 and 3 are same as the finite model, except we have an infinite number of quantities to deal with. So under this model, as with many Bayesian models, it's difficult to compute the posterior distribution. We use variational inference. we specifically tie the variational distributions after level T to their priors, following a technique used by Kurihara et al. And the key point here is that the algorithm that results from this needs to only iterate over non-zero observations and scales to large data sets. A small detail here is we also use auxiliary variables for inference. The only thing I'd mention here is how this helps us is we can set the variational family for these ZUIs that we have introduced to be from multinomial parameterized by these phi parameters. This is the algorithm. It's a coordinate descent algorithm, and we end up having closed form updates for all of our variational parameters because of certain assumptions that we make in the family. And the net result is the computational cost is order of T times R, where T is the truncation level we've chosen in order to truncate the variational family. We don't truncate the model. And R is the total number of non-zero ratings in the matrix. Notice that this is actually the same cost as it is for a finite model. So we ran this Bayesian nonparametric Possion factorization model and the finite model on 2 large movie data sets, the Netflix with 100 million ratings and Movie Lens with 10 million ratings. And on each, we are interested in precision, recall, and the predictive log likelihood. The blue dots correspond to a single run of the finite model where we've set the latent dimensionality, where we vary the latent dimensionality from 10 to 200. And the dashed red line corresponds to a single run of the infinite model. And as we can see here, the infinite model outperforms the finite model in all of these instances. But there is this question of why is there a gap between the infinite model and the finite model? I mean, you'd expect at some point it does just touch the performance of the finite model. We believe this is due to a difference in the prior on these 2 models. And there is, in the case of the infinite model, we do have a size-biased sample of the user weights, which we do not have with the finite model. The infinite model also scales as well as the finite model. The red line converges in 15. I mean, the red line corresponds to convergence of the infinite model in 15 hours, which is around the same order of time that the finite model takes when set with a similar number of latent dimensionality. So in summary, our efficient variational inference algorithm for the Bayesian nonparametric Possion factorization model scales to massive data sets while predicting well. And we believe that both the models, the finite and the infinite models, can be efficient building blocks for more sophisticated models. For example, incorporating time, our user preferences especially tend to change over time. So that's a realistic thing that you would want to model. So there's a number of interesting things we could do with this. Here are the publications and the source code. Thanks.
Questions?
So, Prem, good talk.
Sorry.
So you said that you made this statement that when the ratings are 0, you don't need to explicitly take them into account with the Poisson model. And also another question is that the next step, which I feel here, and is taking it to a stochastic variational thing. And are you guys thinking about it, or?
Yeah, good question. So the Poisson, here what we're doing is treating the entire matrix as observations. So we are treating both the zeros and in the case of implicit data, you have just ones, or in the case of ratings, you have positive quantities. So the entire matrix is treated as observations. That's our approach to dealing with missing data. The second question, we want to develop stochastic variational inference.
You said you compared to the method in Gopalan. What was that method? And it has some generative method for figuring out how many ratings each user has in there?
So it's equivalent to probabilistic matrix factorization with bias terms for users and items. And they use stochastic gradient descent to fit it. I'm not sure if they do anything more to that.
But your graph had number of users and number of ratings in it?
So you're talking about this one?
No, the next one.
This one?
Yeah, user activity is number of...
User activity is the total ratings that the user has given to items.
Okay, I didn't know that was part of the VW model.
I mean, the VW model, they subsample some negatives by popularity, and you can also do it uniformly to the Gaussian model. Yeah.
Have you thought about how to address the question of recommendations when, for example, when Netflix has maybe 2 different users who share an account, but they have very different preferencings? So how would your model deal with something like that?
2 users share an account, but they have very different preferences. So the model will not handle that, I think. Because ultimately, that's a question about how do you collect data. Is there a way to collect data in a way that you can distinguish between these 2 users? Maybe I didn't follow your question.
Yeah. So is there a way that your model could adapt in some machine learning context to
Right.
to separate out that users have very different preferencing so that they're probably not the same person?
Yeah, I think this model will not handle that, and I think that's why incorporating some notion of time, because user preferences change over time, and maybe we can incorporate some notion of periodicity. Maybe there's some user who watches it during the daytime, another user watches it during nighttime. But it definitely requires additional modeling.
Okay, let's thank the speaker again.